discuss BMath 2008 problem. So it's problem number 6, which says that let n choose k be the binomial coefficient, which you already know, it's n factorial divided by k factorial times n minus k factorial. So and fm be the Fibonacci sequence, mth Fibonacci number, and f1 and f2 are given to be both 1, and fm plus 2 is basically the sum of the previous two terms, that is fm plus fm plus 1. As usual, we know how the Fibonacci sequence is generated, the recurrence relation, and so we have to show that summation n choose k is equal to fm plus 1 for all m greater than equals to 1. But there is some condition, that is here the above sum is over all pairs of integers n greater than equals to k greater than equals to 0. So that's the normal condition for the binomial coefficient, but there is another condition with n plus k equals m. So if for f m plus 1, notice that it's n plus k should be equals to m. Okay, that's what we have to prove. So the idea is basically to show that this summation n choose k, whatever be the with the given condition, if we can show that it's satisfying the recurrence relation of the Fibonacci sequence, then we would be done. Okay, so in the Fibonacci sequence, the recurrence relation, you know that fm plus 2 is equal to fm plus 1. So why don't we start with the left hand side, okay, fm plus 2, okay, and then proceed. So for fm plus 2, as you can very well understand, like for fm plus 1, we have to go for n plus k equals m. Okay, so now we are basically backtracking, okay, and here we get an idea, that is what has been given to prove is that for fm plus 1, n plus k should be equals to m. So for this fm plus 2, we know that if we prove this, if this is correct, then for m plus 2, this it should be n plus k equals m plus 1, right? So so let's start with that, and let's show that that summation satisfies the recurrence relation. Okay, so let's go down. Yeah, so let's start with the sum. So summation n choose k n greater than equals to k greater than equals to 0, and n plus k is equals to m plus 1. Okay, so this is where we are starting at. Okay, now this I can write it as equal to, now you must be knowing one very important identity, that is n choose k is equals to n minus 1 choose k minus 1 plus n minus 1 choose k. So this is a very famous combinatorial identity which we are going to use here. Okay, so to break this summation, because we have to show that this summation is nothing but the summation of these binomial coefficient n choose k, where this n plus k would be equal to m. So if for fm we would be having till m minus 1 and then till m. Okay, so we have to divide this sum into two parts, that is one for n plus k equals m minus 1 and the other for n plus k equals m. Okay, so I'll be breaking this sum with the help of this. So now let's see. So, and yeah, this combinatorial identity has a very nice combinatorial argument for the proof. So try it out if you don't know. Okay, so now I can write that this sum is n minus 1, choose k minus 1, n greater than equals to k greater than equals to 1. Okay, because here I mean my n and k when it's n minus 1 and k minus 1, my n and k has to be greater than equals to 1, and the condition n plus k equals m plus 1 plus summation n greater than equals to, okay, let me write down the identity first, n minus 1, choose k. Okay, so now here if you notice that this n minus 1 has to be greater than equals to k. So it basically tells us that n has to be strictly greater than k. So n is strictly greater than k, and k would be greater than equals to 0. So let's take greater than equals to 1 and take the 0 outside, and n plus k is equals to m plus 1. Okay, and for k equals 0, that would be just 1, so let's take it outside. So this is what we are getting, but still it's not in the form that we want. Okay, so for that what we do is so for that what we do is, this is further, so I'm keeping this identity, so let me take this identity outside. Okay, let it be here. Okay, so we are getting this is equal to summation. Now I'll bring this n minus 1, k minus 1 to n choose k. So n choose k. Now, so here n would be greater than equals to k greater than equals to 0, and n plus k would be equal to m minus 1. Okay, so the two variables n and k, they are getting shifted by 1 unit, so the sum gets shifted by 2 units, m minus 1. Okay, and the other sum, that is summation n, so now we can bring that n minus 1 to n, so just shifting of variables. So n choose k, n greater than equals to k greater than equals to 1, and the condition, now one of the variable got shifted by 1, so the sum would just get shifted by 1. So n plus k is equal to m. Okay, so now this is the sum we boil down to. Now we have to bring it down into the form we want. Okay, there was also 1 plus 1. So now this is equals to summation n choose k, n greater than equals to k greater than equals to 0, and n plus k is equal to m minus 1. Okay, and the other one, I'll just bring the 1 again inside and make k equals 0. So summation n choose k n greater than equals to k greater than equals to 1, n plus, sorry, greater than equals to 0 now, and n plus k is equals to m. Okay, so then I think this is the form we want. That is, you see that this is where it's satisfying. Like, what was the left hand side? That it was sum n greater than equals to k greater than equals to 0, n plus k was equal to m plus 1, and choose k, as you can see here. Okay, this is where we started. Okay, so that was the left hand side, right? And so as you can see here, that is, this summation is also satisfying the Fibonacci relation. That is, if I am summing for n plus k equals m plus 1, then whatever that sum is equal to the sum. If I am summing n plus k for n plus k equals, if I am summing n choose k for n plus k equals m minus 1, plus I am summing n choose k for n plus k equals m. Okay, and that proves that, suppose if you had considered that this sum, okay, so this sum in general, if you would have considered Bm to be this sum, that is n greater than equals to k greater than equals to 0, n plus k, or let's say b m plus 2. Okay, so b m plus 2, if we would have said that it's equal to this m plus 1 and choose k, then according to this would have been, this part would have been b. So this is going till m minus 1, right? So this would have been b m, and this is coming till n plus k is m, so this part would have been b m plus 1, and so bm plus bm plus 1 is equals to b m plus 2, right? And thus you see that this summation satisfies the Fibonacci relation, and thus we are done. So yeah, that's it for today. So see you in the next video. Bye.